black hole is often imagined as a perfectly still hole in space, a frozen pit where everything that falls in simply disappears. But that picture is wrong in a deep and fundamental way. In the real universe, nothing is ever truly motionless. Every cloud of gas turns, every star spins, every galaxy drifts and rotates through the dark. Even space-time itself is never at rest. So when a star collapses to form a black hole, it does not lose its motion. It keeps it, it concentrates it, it amplifies it until the rotation becomes so intense that the very fabric of reality is forced to twist around it. This is what a Kerr black hole is. It is a black hole that spins. It is not an exotic or rare type of black hole. It is the normal kind. If a black hole forms from the collapse of a star and nearly all stars rotate, then nearly all black holes must rotate. If two black holes merge, the swirling orbital motion of the pair becomes locked into the final object as spin. The universe has no way to create a large black hole that does not turn, just as it has no way to create a hurricane that does not swirl. When a massive star is born, it forms from a slowly rotating cloud of gas and dust. Even if that rotation is gentle, the laws of physics demand that it speeds up as the cloud shrinks. This is the same effect that causes an ice skater to spin faster when pulling in their arms. As gravity squeezes the star smaller and denser, its rotation rate increases. When the star finally collapses at the end of its life, when nuclear fire can no longer hold gravity back, the core falls inward and the spin becomes extreme. What was once a rotation measured in days becomes a rotation measured in fractions of a second. By the time the event horizon forms, the black hole is already whirling at a significant fraction of the speed of light. This rotation is not just a detail, it is not a minor feature. It changes the entire geometry of space-time around the black hole. A non-rotating black hole, which physicists call a Schwarzschild black hole, bends space-time inward like a deep, spherical well. A rotating black hole does something far stranger. It drags space-time itself around with it, twisting the universe into a vortex. This effect comes directly from Einstein's theory of general relativity. In this theory, mass and energy tell space-time how to curve. Motion and rotation tell space-time how to twist. A spinning mass does not merely sit in space-time, it stirs it. Around a Kerr black hole, this stirring becomes so powerful that nothing in the nearby region can remain at rest relative to the distant universe. Even empty space is forced to rotate. Most black holes in the cosmos are not slow spinners. Observations show that many of them rotate at extraordinary rates. Some stellar mass black holes spin at more than 9/10 of the maximum allowed by the laws of physics. Supermassive black holes in the centers of galaxies also appear to be rapidly rotating, shaped by billions of years of swallowing stars, gas, and even other black holes whose orbital motion feeds into the spin of the final object. The reason spin grows so naturally is that angular momentum is conserved. This means that the universe keeps track of rotation with relentless precision. When matter falls into a black hole, it does not forget that it was moving sideways as well as inward. That sideways motion becomes part of the black hole's spin. Over cosmic time, this builds a rotating monster whose angular momentum can exceed anything else in the observable universe. Once a black hole spins, it can never truly stop. There is no friction in empty space to slow it down. Only by emitting gravitational waves or by interacting with surrounding matter can a black hole lose a little of its spin. But in most environments, it gains far more than it loses. The result is that Kerr black holes are not a special case, they are the rule. And because they spin, they are not simple. The event horizon of a rotating black hole is no longer a perfect sphere. It becomes flattened and stretched. The space-time around it becomes distorted in ways that have no equivalent in ordinary gravity. Paths of light bend into spirals. Orbits become twisted. Even time itself behaves differently, depending on how you move through this warped region. This is why rotation changes everything. A spinning black hole is not just a darker version of a star. It is a machine that converts gravity into motion, motion into energy, and space-time into something that behaves more like a fluid than a stage. Around a Kerr black hole, the universe does not merely curve, it flows. And this is only the beginning of what rotation does. The rotation of a Kerr black hole reaches outward beyond the event horizon, touching the space around it like an invisible hand. This effect is called frame dragging, and it means that the black hole does not simply sit inside spacetime. It pulls spacetime itself into motion. To understand how strange this is, imagine trying to swim in a river whose current is so strong that even the water beneath you is moving. You are not just traveling through the river is carrying you along whether you want it or not. Around a spinning black hole, spacetime becomes that river. Near the black hole, this dragging becomes extreme. An object that tries to hover in place finds that it cannot remain fixed relative to the distant stars. Even if it fires its engines with enormous force, it is still carried sideways by the twisting of space. This is not because of a wind or a force in the ordinary sense. It is because the geometry of the universe itself is rotating. The coordinates of space and time have been warped into a whirlpool. This effect was predicted by Einstein and first worked out in detail by the physicists Joseph Lense and Hans Thirring. It was later confirmed by spacecraft orbiting Earth, which measured how our own planet's modest rotation slightly twists the space around it. But near a Kerr black hole, this same effect grows to unimaginable strength. The twisting becomes so violent that it creates a new region of reality where the very idea of standing still loses its meaning. The deeper you go into this rotating spacetime, the faster everything is dragged. At some distance from the black hole, the dragging is gentle. Farther in, it becomes unavoidable. And closer still, it becomes absolute. There comes a boundary where the twisting is so intense that not even light can resist it. Any beam of light fired against the rotation is forced to curve and eventually move in the same direction as the spin. This region is called the Ergosphere. It sits outside the event horizon, wrapped around it like a lopsided shell. Inside the Ergosphere, no observer can remain stationary relative to the distant universe. You can still move outward. You can still escape if you have enough energy. But you cannot stop rotating with the black hole. The shape of the Ergosphere is not spherical. It bulges outward at the equator, where the spin is strongest, and shrinks at the poles where the rotation has less influence. This shape reveals the deep connection between gravity and rotation. The black hole is not just pulling inward, it is dragging sideways as well. In this region, the rules of physics become deeply counterintuitive. Energy and motion mix together. Paths that once seemed impossible become allowed. The black hole begins to behave like a cosmic engine, capable of giving energy back to the universe instead of only swallowing it. This is one of the most astonishing predictions of general relativity. A rotating black hole can be tapped like a battery. Its spin can be drained. Matter can enter the ergosphere, split apart, and leave behind negative energy that reduces the black hole's rotation, while another part escapes with more energy than it started with. In effect, the black hole gives up some of its rotational power. This is not science fiction. It is a direct consequence of the way space-time behaves when it is forced into a vortex. The ergosphere exists because the black hole refuses to sit still. It is the physical imprint of motion on the structure of reality. And beyond this region lies something even more extreme. Beyond the ergosphere, the twisting grows stronger still. Space and time are pulled so hard that they begin to trade roles. Directions that once pointed outward now point inward. The simple idea of distance loses its clarity. The black hole does not merely trap matter, it reshapes what it means to move at all. This is why a Kerr black hole is not just a darker version of any other object. It is a laboratory where gravity, motion, and time are fused into a single phenomenon. It is where the universe shows how deeply it can bend its own rules without breaking them. As one moves closer to a spinning black hole, the twisting of space-time becomes so strong that it begins to dominate every possible path. Light, matter, and even the flow of time are pulled into the same rotational current. What makes this so profound is that nothing special is required to feel this effect. You do not need to be touching the black hole. You do not need to cross the event horizon. The very structure of space around it is already in motion, and anything that exists within that region must follow. This reveals a deeper truth about gravity in the universe. Gravity is not just a force that pulls objects together. It is a shaping of space-time. When an object spins, that shaping includes a twisting. Near a Kerr black hole, the twist becomes so extreme that the geometry itself behaves like a whirlpool. Every possible future is tilted in the direction of the spin. Imagine trying to move in a place where the floor beneath you is rotating faster and faster as you approach the center. At first, you can walk against it. Then you are forced to turn slightly. Eventually, you are carried along, no matter how hard you try. Near the event, horizon of a rotating black hole, this becomes absolute. There is no path that does not spiral inward. Yet even here, outside the horizon, escape is still possible. You can still move away if you travel faster than the dragging of space-time. But the cost in energy rises sharply. The closer you get, the more of your effort goes into fighting the rotation rather than moving outward. This creates a natural boundary where physics becomes a balance between motion and geometry. This boundary is what separates the ordinary universe from the strange domain where the black hole begins to give up its secrets. It is here that energy extraction becomes possible. It is here that the black hole shows that it is not just a one-way sink, but a rotating reservoir of gravitational power. The universe uses this power. Around many Kerr black holes, swirling disks of gas form. As this matter falls inward, it is dragged into rapid rotation. Magnetic fields become twisted and amplified. Beams of particles are launched outward at nearly the speed of light, forming jets that can stretch across entire galaxies. These jets are not powered by the mass of the black hole alone. They are powered by its spin. The rotation of space-time acts like a giant flywheel. It stores energy, it releases it. It shapes the environment on scales far larger than the black hole itself. A single supermassive Kerr black hole can influence the growth of an entire galaxy by controlling how gas flows and how stars are born. All of this begins with a simple fact. The black hole refuses to sit still. It is not an object in space. It is a region of space-time that is in motion. And because space-time is the stage on which all physics plays out, that motion affects everything that comes near. This is why the study of Kerr black holes is not just about gravity. It is about understanding what space and time are allowed to do. It is about exploring the limits of Einstein's equations. It is about seeing how the universe behaves when its deepest structures are pushed to their extremes. The rotation of a black hole is not a side effect. It is the source of its most astonishing properties. It creates the ergosphere. It enables energy extraction. It bends light into spirals. It warps time itself. And deeper inside, beyond what we can see from the outside, it leads to even stranger regions where the geometry of reality becomes unstable and mysterious. The black hole that refuses to sit still is not just one of many types. It is the true face of black holes in the universe. It is the form that nature almost always creates. And it is the gateway to some of the most extreme physics that can exist. The most unsettling truth about a rotating black hole is not that matter is dragged around it, but that space itself is. In everyday life, we imagine space as a quiet background, a passive stage on which planets and stars move. Near a Kerr black hole, that idea collapses. Space becomes active. It begins to flow. It begins to rotate. The universe around the black hole is no longer something that objects move through. It is something that carries them. This effect is called frame dragging. It means that the coordinate grid of space and time is pulled along by a spinning mass. If a planet spins, it drags the space-time around it a tiny amount. If a neutron star spins, the effect is stronger. If a black hole spins, the effect becomes overwhelming. The geometry of the universe itself is forced into motion. This is not a metaphor. It is a precise prediction of general relativity. When mass and energy move, they create not only curvature, but also twist. That twist changes the way paths are defined. It changes how clocks tick. It changes how straight lines are drawn. Near a Kerr black hole, the twisting becomes so intense that the future of every object is tilted in the direction of the spin. Imagine releasing a small probe near such a black hole. You give it no sideways motion at all. You only let it fall straight inward. From the perspective of distant space, it will still begin to move sideways. Not because of a force in the ordinary sense, but because the coordinates of space are rotating beneath it. The probe is following the straightest possible path through a twisted geometry. This reveals something profound. Motion near a black hole is not just about velocity, it is about geometry. What we call gravity is really the shape of space-time telling objects how to move. When space-time itself is rotating, motion becomes inseparable from the structure of the universe. The Lense-Thirring effect is the name given to this twisting of space-time by rotation. It was first measured around Earth using satellites and gyroscopes. The effect is extremely small for a planet, but it is real. Earth drags the space around it by a tiny fraction. Near a Kerr black hole, the same effect grows by orders of magnitude until it dominates everything. This is why the region around a spinning black hole feels less like empty space and more like a fluid. In a fluid, motion in one place drags the surrounding material along. Vortices form, currents develop. Near a black hole, space-time behaves in the same way. The rotation of the central mass sets up a whirlpool in the geometry of the universe. As you move closer to the black hole, this whirlpool tightens. The speed of the space-time flow increases. There comes a distance where even light cannot swim against the current. At that point, the twisting of space has become stronger than the fastest possible motion through it. This is where a new region of physics begins to appear. It is not yet the event horizon. You are not yet trapped. But you are no longer free to choose your state of rest. The universe itself has taken that choice away. Here, the idea of being stationary loses its meaning. There is no place you can hover without moving. The space-time you are trying to stay within is already in motion. This is the first sign that a Kerr black hole is not just a gravitational object, but a dynamical structure that reshapes the concept of space itself. The twisting of space-time does not fade abruptly. It grows smoothly as you approach the black hole. Far away, the effect is gentle. Near the black hole, it becomes violent, and at a certain boundary, it becomes absolute. That boundary is where the Ergosphere begins. Before reaching it, you can still fight the flow. You can still move against the rotation with enough energy. But the cost rises rapidly. The closer you go, the more of your effort is spent resisting the twist rather than moving where you want. This is the point where gravity and rotation become indistinguishable. The pull inward and the drag sideways merge into a single geometric force. The black hole is no longer just drawing things toward it, it is sweeping them into a cosmic spiral. And it is this spiral that opens the door to some of the strangest phenomena in the universe. The deeper you fall into the rotating space-time around a Kerr black hole, the more the universe begins to feel like a moving medium rather than empty nothingness. Every direction you look has been tilted. Every possible path curves. Even the straightest line through this region becomes a spiral. This is because the geometry of space and time has been twisted into a vortex by the black hole's enormous spin. In ordinary gravity, mass bends space inward. In the gravity of a spinning black hole, mass also bends space sideways. This creates a gravitational field that has both a pull and a drag. The pull draws objects closer. The drag forces them to move in the direction of rotation. These two effects cannot be separated. They are both part of the same curved and twisted space-time. To an outside observer, this looks like a force acting on anything that comes near. But in reality, it is not a force at all. Objects are simply following the natural paths that exist in a warped geometry. When space-time itself is rotating, the shortest path between 2 points is no longer a simple line. It is a curve that wraps around the black hole. This is why orbits near a Kerr black hole behave so strangely. A particle that would have followed a simple circular orbit around a non-rotating black hole now finds its path precessing. The orbit slowly twists. The point of closest approach drifts. Over time, the entire trajectory is dragged into alignment with the black hole spin. This effect is not small. Near the black hole, it becomes dramatic. Orbits that would normally be stable become unstable. Paths that would normally lead outward can be turned inward. The black hole does not just wait for matter to fall, it actively reshapes the routes that matter can take. There is a point where this reshaping becomes absolute. At that distance, there is no longer any possible trajectory that remains fixed relative to the distant universe. Every future path leads to rotation. This is where the ergosphere begins. The ergosphere is not the event horizon. You can still escape from it, but you cannot avoid being carried along by the space-time flow. If you try to hold position, you will find that your velocity relative to distant stars is no longer zero. The universe itself is moving around you. Inside this region, energy behaves in a strange way. Because space-time is rotating, the definition of energy relative to infinity changes. Some paths that would normally require energy now release it. Some states that would normally be impossible become allowed. This is what makes energy extraction from a Kerr black hole possible. It is not because the black hole is leaking. It is because the geometry of space-time allows matter to have negative energy relative to the outside universe. When such matter falls in, it reduces the spin of the black hole. The missing energy reappears outside as a gain for escaping material. This is one of the deepest results of general relativity. A black hole is not just a sink. It is a dynamical object that can exchange energy with its surroundings through the twisting of space-time. The ergosphere exists only because the black hole spins. A non-rotating black hole has no such region. There, space-time only falls inward. It does not swirl. Without rotation, there is no way to extract energy. But with rotation, the black hole becomes a machine, a gravitational turbine powered by the most extreme form of angular momentum in the universe. The closer you move toward the event horizon, the stronger this effect becomes. The space-time flow accelerates, the energy available from the spin grows, and the paths that lead inward and outward become more and more distorted. By the time you reach the inner boundary of the ergosphere, you are standing at the edge of a domain where even light is forced to move with the black hole. Beyond that, the universe tilts so far that all futures point inward. This is where the black hole truly begins. As the ergosphere wraps around the rotating black hole, it marks the place where the universe has been pushed beyond any familiar idea of rest. Here, even empty space is in motion. Light cannot remain fixed. Matter cannot hover. Every possible future carries a sideways drift imposed by the twisting of space-time itself. This is not a region defined by matter or by radiation. It is defined by geometry. The event horizon lies deeper still. It is the surface where the inward flow of space-time reaches the speed of light. At that boundary, not even a beam of light can climb back out. But long before reaching it, the ergosphere has already taken away the freedom to remain still. It has already rewritten what it means to move. This layered structure reveals the true complexity of a Kerr black hole. It is not just a point of no return. It is a system of regions, each with its own rules, created by the interaction of gravity and rotation. The outer universe sees a black hole as a simple dark object, but up close, it is a storm in the fabric of reality. The twisting of space-time near the black hole is so intense that the usual distinction between space and time begins to blur. Directions that once pointed sideways now point toward the future. Motion through space becomes entangled with motion through time. To move in one direction is to move in the other. This is not poetic language. It is a literal property of the equations of general relativity. Near a Kerr black hole, the coordinate that represents time mixes with the coordinate that represents rotation. The result is that the future itself becomes curved around the black hole. This is why escape becomes harder and harder. It is not just that gravity is pulling you in. It is that the geometry of time is tilting toward the black hole. Your future is being bent. Yet even here, the black hole is still giving something back. The rotation that traps you is the same rotation that powers some of the brightest objects in the universe. Around many Kerr black holes, disks of hot gas shine with extraordinary intensity. Jets of particles stream outward for millions of light years. These are not powered by simple infall. They are powered by the extraction of spin energy from the black hole itself. Magnetic fields thread the swirling plasma. They tap into the rotating space-time. They carry energy outward along narrow beams. The black hole becomes a cosmic generator, converting gravity and rotation into radiation. This is how quasars shine. This is how active galactic nuclei reshape their host galaxies. At the heart of these phenomena lies the same simple truth. The black hole is spinning, and space-time is forced to spin with it. The universe has few places where its deepest principles become so visible. In the Kerr geometry, gravity is no longer just attraction. It is motion. It is rotation. It is the shaping of time itself. And beyond the event horizon, deeper still, this twisting leads to even stranger structures, inner horizons, ring-shaped singularities, paths through space-time that defy ordinary causality, but those lie further in, beyond what we can see from the outside. For now, what matters is this. A Kerr black hole is not a static object. It is a dynamic region of space-time in motion. It drags the universe into a whirlpool. It creates new domains of physics. It turns gravity into a source of energy. When space itself starts to spin, the universe reveals just how flexible its own fabric can be. The Ergosphere is one of the strangest regions ever predicted by physics. It is not a solid surface, and it is not a wall. It is a volume of space where the motion of the universe itself becomes unavoidable. Around a rotating black hole, this region forms a swollen shell outside the event horizon, shaped by the furious spin of space-time. To understand why it exists, one must let go of the idea that space is still. In the presence of a Kerr black hole, space is in motion, and inside the Ergosphere that motion becomes absolute. Far from the black hole, space-time is only gently twisted. You could float there and remain almost at rest relative to the distant stars. As you move closer, the twisting grows stronger. Eventually you reach a boundary where even light can no longer remain stationary. At that distance, the rotation of space-time is so intense that every possible path through the future includes motion in the direction of the black hole spin. That boundary marks the outer edge of the Ergosphere. Inside it, there is no such thing as standing still. You can fire your engines, you can struggle, you can try to hold position, but the geometry of space-time itself is carrying you along. Even if you try to remain fixed relative to the rest of the universe, the coordinates of space are already rotating beneath you. Your attempt to stay in place becomes meaningless. This does not mean you are falling inward. You can still move outward. You can still escape if you have enough energy. But you cannot avoid rotating. The black hole has claimed your sideways motion. The shape of the Ergosphere reveals how rotation warps reality. It is not a simple sphere. It bulges outward at the equator where the spin is strongest. It narrows at the poles where the rotation has less effect. This lopsided geometry shows that the black hole is not just pulling in, it is dragging around. The reason this happens lies in the way time itself is bent. In the equations of general relativity, time and rotation become linked near a Kerr black hole. The coordinate that measures time mixes with the coordinate that measures angular motion. This means that to move forward in time inside the ergosphere is to move around the black hole. There is no future that does not include rotation. This mixing of time and motion creates something extraordinary. It allows energy to become negative relative to the distant universe. In normal space, energy is always positive. It costs energy to move. It costs energy to exist. But inside the ergosphere, because space-time itself is rotating, some states of motion subtract energy from the black hole instead of adding to it. This is not magic, it is geometry. The black hole has so twisted space-time that the usual definitions of energy no longer apply in the same way. Paths that look impossible from far away become allowed here. Imagine a particle falling into the ergosphere. If it splits into two pieces, one can be forced into a state of negative energy, relative to infinity. That piece falls into the black hole, reducing its spin. The other piece escapes with more energy than the original particle had. The extra energy comes from the black hole rotation. This means the ergosphere is not just a strange region. It is a gateway to extracting power from a black hole. The black hole is not simply swallowing, it is also giving. This possibility changes how we see these objects. A rotating black hole is not a dead end. It is an engine. It stores enormous amounts of rotational energy. For a rapidly spinning black hole, this energy can rival a significant fraction of its total mass energy. That energy can in principle be tapped. In the real universe, it is tapped by magnetic fields and plasma rather than by simple particles. Gas falling toward the black hole becomes ionized. Magnetic lines of force thread the ergosphere. The rotation of space-time twists these fields like rubber bands. They snap back and fling energy outward. This process powers the jets that blaze from the centers of galaxies. None of this would be possible without the ergosphere. Without this region, where nothing can stand still, a black hole would be a simple sink. With it, a black hole becomes one of the most powerful energy sources in the cosmos. The ergosphere sits outside the event horizon. It is a zone of extreme physics that can still communicate with the rest of the universe. Light can escape, particles can leave, information can flow. But inside it, every path is bent by the same inexorable twist. Even light is forced to move. A beam fired against the spin will be dragged around. Its path curves. Its direction changes. The geometry of space-time itself is steering it. This is why the ergosphere feels less like empty space and more like a moving medium. It is a place where the universe itself has a current. And deeper still, beyond the inner edge of this region, lies the event horizon. There, the inward flow of space-time reaches the speed of light. There, the last escape route's close. But the ergosphere is the first sign that a Kerr black hole is not just a trap. It is a machine. It is where rotation becomes a physical force and where the rules of energy are rewritten. As one moves deeper into the ergosphere, the experience would become increasingly unreal. The sky would no longer look like a distant sphere of stars. Light from every direction would be bent and dragged. Images of the universe would stretch and smear into arcs around the black hole. Some stars would appear in multiple places at once as their light loops around the rotating space-time before reaching your eyes. What you see would no longer match where things truly are, because the geometry of the region has twisted every path that light can take. Inside this zone, the very idea of a straight line disappears. Even if you shine a laser, it will not travel in a simple direction. It will curve as it moves because space-time itself is rotating beneath it. The faster the black hole spins, the more severe this effect becomes. For the most rapidly rotating Kerr black holes, the ergosphere extends far from the event horizon, creating a vast region where the universe is in constant motion. Time behaves just as strangely here. Clocks that try to remain fixed relative to the distant stars cannot do so. Their flow of time is tied to their motion around the black hole. To exist inside the ergosphere is to be caught in a current of time as well as space. Your future is forced to follow the spin of the black hole. This is why no static observers can exist in this region. It is not that some force pushes you. It is that the geometry of time itself is rotating. To stay in one place would require moving backward in time, which is not allowed. Every allowed future points in a direction that includes motion around the black hole. Yet despite this strangeness, the ergosphere is not fatal. You can survive here. You can even leave. With enough energy, you can climb back out to ordinary space-time. But you will leave with a new understanding of what motion really means. You will have felt space itself flowing around you. This region is also where the black hole interacts most strongly with its surroundings. Gas and dust that fall toward the black hole are pulled into rapid rotation. Their kinetic energy rises. Friction within the swirling disk heats the material until it glows with intense radiation. Much of the light we see from black holes is actually emitted far outside the event horizon in this violently rotating environment. The ergosphere plays a key role in this process. It is where space-time gives some of its rotational energy to matter and fields. Magnetic lines become twisted. Particles are accelerated. The black hole begins to act like a generator embedded in the universe. This is why the brightest objects in the cosmos often sit at the hearts of galaxies, where Kerr black holes spin. Quasars, blazars, and active galactic nuclei all draw their power from this same source. Not from the mass of the black hole alone, but from its rotation and from the strange geometry of the ergosphere that makes energy extraction possible. In a deep sense, the ergosphere is a bridge between the simple gravity of falling inward and the complex physics of rotation. It is where the black hole stops being a passive object and becomes an active participant in cosmic evolution. Without this region, black holes would simply swallow. With it, they shape galaxies. They regulate star formation. They inject energy into interstellar space. A single spinning black hole can influence billions of suns worth of matter through the geometry of space-time alone. And all of this begins in a place where nothing can stand still. At the inner edge of the ergosphere, the twisting of space-time reaches a level that feels almost absolute. Here, the flow of the universe has become so fast that even light aimed directly outward must struggle to make progress. The black hole is not just pulling you inward. It is sweeping the very fabric of reality past you. Every possible path is bent. Every future is tilted. This is the boundary where the ergosphere meets the event horizon. It is a surface defined not by matter, but by motion. Beyond it, the inward flow of space-time exceeds the speed of light. Once that happens, no signal and no particle can ever return. The horizon is not a wall. It is a one-way current in the geometry of the universe. From the outside, the event horizon looks like a smooth, dark sphere. But from within the ergosphere, it feels like the center of a vast whirlpool. You are not being pushed through it. You are being carried by the structure of space-time itself. The ergosphere is what allows the black hole to give energy back to the universe. But the event horizon is what enforces its role as a trap. Together, they form a system where gravity and rotation combine into something that has no parallel anywhere else in nature. The black hole has become a machine. Matter falls in, energy flows out, space-time spins, light bends, time itself is dragged. Yet all of this complexity is hidden from far away. To a distant observer, the black hole is defined only by its mass, its spin, and its electric charge. Everything else about it is invisible behind the horizon. The wild dynamics of the ergosphere, the violent twisting of space-time, the exchange of energy, all of it is cloaked behind a simple, dark silhouette. This is one of the great ironies of black holes. The most extreme and intricate physics in the universe occurs in regions that are almost impossible to observe directly. We infer their existence from the light of the accretion disk, from the shape of the shadow, from the power of the jets. But the ergosphere itself remains hidden, a ghostly zone defined only by the equations of relativity. Still, those equations are clear. A Kerr black hole cannot avoid creating this region. The moment it spins, space-time must twist. And where space-time twists strongly enough, the ergosphere must appear. This makes the ergosphere not just a curiosity, but a fundamental feature of rotating gravity. It is where the universe reveals that motion and energy are woven into the geometry of time and space. And beyond this region lies an even stranger domain. Inside the event horizon, the black hole continues to rotate. Space-time continues to twist. But the rules that govern cause and effect begin to change in ways that push the limits of what physics can describe. There, deeper in, lie the inner horizon and the ring-shaped singularity. Places where time and space exchange roles. Places where paths loop in ways that seem to allow travel into the past. Places where the equations of relativity predict structures that may not be stable or even real. The ergosphere is only the outer warning that such regions exist. It is the last place where the universe still resembles anything we know. A rotating black hole contains more than mass. It contains motion. That motion is stored in the twisting of space-time itself. And because space-time is not rigid, because it can be stretched and bent and rotated, that stored motion can be transferred. A Kerr black hole is not just an absorber of energy, it is a reservoir of rotational power. This idea seems impossible at first. How could anything escape from a black hole with more energy than it had when it fell in? The answer lies in the strange geometry of the ergosphere. Inside that region, the definition of energy is no longer what it is in ordinary space. The twisting of time and space allows certain paths to carry negative energy relative to the distant universe. This does not mean that the particle has less than nothing. It means that its motion subtracts from the black hole spin. When such a particle falls into the black hole, it reduces the total angular momentum of the black hole. The missing energy appears outside as an increase in the energy of escaping matter. This process was first described by the physicist Roger Penrose. It is called the Penrose process. In its simplest form, a particle enters the ergosphere and splits into two. One piece is forced into a path of negative energy and falls into the black hole. The other escapes with more energy than the original particle had. The extra energy comes directly from the rotation of the black hole. This is not a trick. It is a direct result of the way space-time is shaped in the ergosphere. The black hole is losing spin. The universe is gaining energy. In theory, a Kerr black hole can lose up to about 29% of its total mass energy through this process if it starts out spinning as fast as the laws of physics allow. That is an extraordinary amount of power. For a supermassive black hole, it represents more energy than entire galaxies radiate over their lifetimes. In practice, nature uses a more efficient version of this process. It involves magnetic fields and plasma rather than individual particles. Gas falling toward a black hole forms a disk. That disk becomes threaded by magnetic fields. As the black hole rotates, it drags those fields with it. The twisting of space-time twists the magnetic lines of force. They store energy like stretched springs. When they snap back, they launch particles outward in narrow beams called jets. This mechanism is known as the Blandford-Zenarjek process. It is the main engine behind the relativistic jets that shoot out from the centers of active galaxies. These jets can extend for millions of light years. They carry enormous amounts of energy. They influence the formation of stars. They heat intergalactic gas. They shape the evolution of galaxies. All of this power comes from the spin of the black hole. The black hole is not consuming matter to produce this energy. It is consuming its own rotation. As energy is extracted, the black hole spins more slowly. Its ergosphere shrinks. Its ability to drive jets weakens. This creates a natural life cycle. A black hole that is fed by a steady flow of matter spins up. Its jets grow powerful. It becomes an active galactic nucleus. When the flow of matter slows, the black hole loses spin. The jets fade. the galaxy enters a quieter phase. The universe uses Kerr black holes as regulators. They are cosmic engines that turn gravitational collapse into light, heat, and motion on the largest scales. This ability to give energy back to the universe is unique to rotating black holes. A non-rotating black hole has no ergosphere. It has no region of negative energy. It cannot be tapped in this way. Only a Kerr black hole can act as a generator. This is why rotation is not just an extra detail. It is the source of some of the most dramatic phenomena we observe. Every quasar, every blazar, every radio galaxy owes its brilliance to a black hole that refuses to sit still. The power that flows from a rotating black hole is not gentle. It is among the most intense energy releases in the universe. Near the event horizon, magnetic fields become twisted into tight coils by the rotating space-time. Charged particles are caught in these fields and hurled outward at nearly the speed of light. As they travel, they emit radiation across the entire electromagnetic spectrum, from radio waves to high-energy gamma rays. These jets are so focused that they can travel across intergalactic space without dispersing. Some stretch for millions of light years, piercing through the gas between galaxies. Wherever they pass, they heat the surrounding matter and change the conditions for star formation. A single Kerr black hole can therefore shape the destiny of an entire cluster of galaxies through the energy it releases from its spin. This process is deeply tied to the geometry of the ergosphere. The twisting of space-time makes it possible for magnetic fields to extract energy. Without that twisting, the fields would simply slide through space. With it, they become anchored to the rotation of the black hole itself. They act like a mechanical connection between the black hole and the distant universe. As the black hole spins down, this connection weakens. The ergosphere shrinks. The amount of energy that can be extracted declines. Over cosmic time, if a black hole were isolated, it would eventually become nearly non-rotating. It would become a simple Schwarzschild black hole. But in the real universe, black holes are rarely isolated. They continue to accrete matter. They merge with other black holes. Their spin is constantly being refreshed. This creates a dynamic balance. Some black holes are rapidly rotating, powering brilliant jets. Others are slower, quieter, and darker. By measuring the spin of black holes, astronomers can learn about their history. A fast spin suggests a long period of steady accretion or a major merger. A slow spin suggests a chaotic past with matter falling in from many directions. Spin has become one of the most important parameters in black hole astrophysics. It influences how close matter can orbit before plunging in. It determines how much energy can be extracted. It shapes the appearance of the black hole shadow. It even affects how gravitational waves are emitted when black holes collide. All of these effects trace back to the same simple fact. The black hole is rotating. And because space-time is the medium of all physics, that rotation reshapes everything around it. The Penrose process and the Blandford-Znajek mechanism are not just theoretical curiosities. They are the engines behind some of the brightest lights in the sky. When we see a distant quasar blazing with the power of trillions of suns, we are seeing the rotational energy of a Kerr black hole being converted into radiation. In this way, black holes are not the end of the story of matter. They are part of the cycle of cosmic energy. They gather mass, they spin, they release power, they influence their environment. They are both destroyers and creators on the grandest scales. The idea that a black hole can give something back to the universe is one of the most surprising lessons of modern physics. It shows that even the darkest objects are woven into the flow of cosmic energy. And deeper inside, beyond the horizon, the rotation continues. There, the geometry becomes even more strange. There, the very notion of energy may lose its meaning entirely. As energy is drawn from a rotating black hole, the black hole itself changes. Its spin slows, its ergosphere shrinks. The shape of its event horizon becomes less flattened. Over long periods of time, if no new matter falls in, a Kerr black hole will gradually approach a non-rotating state. In that final condition, it can no longer give up energy. It becomes a quiet gravitational well. But the universe almost never allows this to happen. Black holes are born in chaos. They live in environments filled with gas, stars, and other black holes. Each time something falls in, it brings angular momentum. Each time two black holes merge, their orbital motion becomes spin. The black hole is constantly being wound up again. This creates a feedback loop. The more a black hole spins, the more efficiently it can power jets. The jets then influence the flow of matter in the surrounding galaxy. They can blow gas away or heat it so that it cannot collapse into new stars. In this way, the spin of a single black hole can regulate the growth of billions of stars. This is why Kerr black holes are not just curiosities. They are central players in cosmic evolution. Without their rotational energy, galaxies would grow and evolve in very different ways. The ability to steal energy from a black hole is one of the deepest insights of modern astrophysics. It tells us that gravity is not just a sink, it is a dynamic system. When combined with rotation, it becomes a source of power. Yet this power comes from something deeper than magnetic fields or plasma. It comes from the structure of space-time itself. The black hole has turned geometry into fuel. This idea reaches its most extreme form inside the event horizon. There, the rotation does not stop. Space-time continues to twist. But the meaning of energy becomes obscure. The future is forced inward. And new horizons appear. Beyond the outer horizon lies an inner horizon. Beyond that lies a ring-shaped singularity. In those regions, the equations of general relativity predict behaviors that challenge our understanding of cause and effect. The black hole that gives energy to the universe on the outside becomes a place where reality itself may break on the inside. The power of a Kerr black hole is therefore two-sided. On one side, it lights up the cosmos. On the other, it hides some of the deepest mysteries in physics. Stealing energy from a black hole is only the beginning of what rotation makes possible. Beyond the event horizon of a rotating black hole lies a region that no telescope can ever see, yet whose existence is written clearly in the equations of general relativity. Inside a Kerr black hole, space-time does not simply collapse toward a single point, it continues to twist. The rotation that shapes the ergosphere outside the horizon also shapes the deep interior in ways that have no counterpart in non-rotating black holes. In a non-rotating black hole, all paths lead to a single central singularity. It is a place where density becomes infinite and the known laws of physics break down. In a Kerr black hole, the singularity is not a point, it is a ring. It lies in the equatorial plane, like a loop embedded in the fabric of space-time. This ring singularity is a direct consequence of rotation. The black hole has so much angular momentum that it cannot collapse into a single point. Instead, space-time wraps around itself, leaving a circular region where curvature becomes infinite. As you fall inward, you do not encounter this ring immediately. First, you cross the event horizon. Beyond it, the future points inward. You are carried deeper no matter what you do. But then, something strange happens. Instead of continuing smoothly to the singularity, you encounter another boundary. This is called the inner horizon. It is a surface where the structure of space-time changes again. The inward flow of time slows. The geometry becomes unstable. Paths that were once forced toward the singularity can, in theory, change direction. The existence of this inner horizon is one of the most bizarre predictions of the Kerr solution. It suggests that inside a rotating black hole, there may be regions where the roles of space and time swap back and forth. In some of these regions, it may even be possible to avoid hitting the singularity. According to the mathematics, some trajectories can pass through the ring singularity without encountering infinite density. Because the singularity is a ring and not a solid wall, there is a hole at its center. A path that threads that hole might emerge into another region of space-time. This has led to speculation that Kerr black holes might contain passages to other universes or to other times. The equations allow closed time-like curves, paths through space-time that loop back on themselves. In such a geometry, it may be possible in principle to return to your own past. But these predictions come with a warning. The inner horizon is violently unstable. Any small disturbance grows without bound. Radiation falling into the black hole becomes infinitely blue-shifted. Energy piles up. The structure predicted by the simple equations of general relativity may be destroyed by these effects. Most physicists believe that the inner horizon would become a region of extreme turbulence, perhaps turning into a new kind of singularity. The elegant picture of smooth passage through a ring may not survive in the real universe. This is where our understanding reaches its limits. The Kerr solution is a beautiful mathematical object. It tells us what space-time would look like around an ideal rotating black hole. But real black holes are never perfectly isolated. They are surrounded by matter and radiation. Those influences may radically alter the deep interior. Still, the fact that such strange structures appear in the equations is telling. It suggests that rotation pushes gravity into a regime where time and space lose their familiar roles. The black hole interior becomes a place where causality itself can be twisted. The ring singularity and the inner horizon are the ultimate expression of the black hole refusal to sit still. The same spin that powers jets and drags spacetime outside also creates a labyrinth of warped geometry inside. Whether these regions truly exist or are replaced by something even more extreme is one of the great open questions in physics. As one moves deeper past the inner horizon, the nature of spacetime becomes increasingly difficult to describe with ordinary language. The future no longer points in a single simple direction. Instead, it branches and twists. Paths that once led inevitably toward the singularity may in theory bend away. The geometry predicted by the Kerr solution allows for corridors through spacetime that curve back on themselves. In these corridors, time and space exchange roles in a way that seems to permit loops through causality. This is where the idea of closed time-like curves arises. A closed time-like curve is a path through spacetime that returns to the same event from which it started. In such a geometry, an object could in principle meet its own past. This is not a fantasy added by science fiction writers. It emerges directly from the equations that describe a rotating black hole. The ring-shaped singularity at the center of a Kerr black hole plays a key role in this strange structure. Because the singularity is not a point but a loop, there is a region inside, that loop where space-time is not crushed to infinite density. The equations suggest that a traveler passing through this region could avoid the singularity and emerge into another part of the geometry. Some mathematical extensions of the Kerr solution show entire new universes connected through this ring. Others show regions where time flows in reverse relative to the outside world. These are not interpretations added by humans. They are literal consequences of how the equations behave when rotation is included. Yet there is a problem. The inner horizon that guards this region is unstable. Any small amount of radiation falling into the black hole becomes infinitely amplified as it approaches this boundary. Light from the outside universe is compressed into shorter and shorter wavelengths. Its energy grows without limit. This creates what is known as mass inflation. The space-time becomes violently distorted. Because of this instability, most physicists believe that the elegant structure, predicted by the ideal Kerr solution, would collapse into something far more chaotic in a real black hole. The inner horizon might become a new kind of singularity. The smooth passage through the ring might be destroyed by intense gravitational turbulence. This is where general relativity may no longer be sufficient. The densities and energies involved are so extreme that quantum effects must become important. But no complete theory of quantum gravity yet exists. We do not know how space-time behaves when curvature and energy reach these limits. What we do know is that rotation drives black holes into a far more complex regime than simple collapse. A non-rotating black hole hides a single central singularity. A rotating one hides an entire internal universe of warped geometry. The inner horizon and the ring singularity represent the deepest expression of the black hole spin. The same angular momentum that twists spacetime outside into an ergosphere and powers cosmic jets also twists the interior into a labyrinth of possible futures. In this sense, a Kerr black hole is not just an object. It is a dynamic structure of spacetime that extends from the observable universe into realms that may never be directly tested. The questions raised by this interior are some of the most profound in physics. Does time really loop inside a rotating black hole? Can information escape through these hidden corridors? Does the singularity resolve into something finite when quantum effects are included? For now, these remain open mysteries, but the equations are clear on one point. Rotation transforms a black hole from a simple end state into a gateway to the unknown. At the deepest level, the inner structure of a Kerr black hole confronts physics with its own limits. The equations of general relativity describe a rotating geometry that is mathematically consistent yet physically unsettling. They allow time to curve back on itself. They allow paths that seem to evade the singularity. They predict a ring where density becomes infinite, but not everywhere, leaving a hollow center through which space-time might continue. This is not how gravity behaves anywhere else in the universe. It is a regime where our usual ideas about cause and effect, before and after, and even existence itself begin to fail. Yet nature may not permit these structures to exist in their pure form. The instability of the inner horizon suggests that the neat corridors and loops predicted by the equations could be destroyed by the slightest disturbance. Real black holes are not isolated mathematical objects. They are fed by matter. They are bathed in radiation. They are shaken by gravitational waves. All of this falls inward and piles up at the inner horizon, potentially creating a new kind of singularity that blocks any passage. If this is true, then the ring singularity might be hidden behind a chaotic barrier, making the exotic predictions of time loops and other universes unreachable. But even if these structures are never physically realized, their presence in the equations tells us something important. It tells us that rotation pushes gravity into a regime far beyond simple collapse. It forces space-time into shapes that test the boundaries of mathematics and physics. It suggests that black holes are not just the ends of things, but gateways to regimes where the laws we know may be replaced by something deeper. The Kerr solution has been studied for decades, and it remains one of the most beautiful and troubling results in theoretical physics. It shows that a single additional property, spin, transforms a black hole from a simple object into a complex universe in its own right. The outer regions of a Kerr black hole give us energy, jets, and radiation. The inner regions give us paradoxes, horizons within horizons, and singularities shaped like rings. Both arise from the same source: rotation. The black hole that refuses to sit still reshapes not only the space around it, but the very meaning of time and causality inside it. And beyond this interior lies the next great mystery: how time itself behaves near and within a spinning black hole. Near a rotating black hole, time is no longer the steady river we experience on Earth. It becomes warped, stretched, twisted, and in some directions even reversed. The same spin that drags space into motion also drags time itself. In the geometry of a Kerr black hole, time and rotation are woven together so tightly that they cannot be separated. Far from the black hole, clocks tick in a familiar way. 1 second follows another. Causes led to effects. But as you approach a spinning black hole, something subtle begins to happen. Your time starts to drift relative to the rest of the universe. An observer far away will see your clock slow down. This is normal gravitational time dilation. But in a Kerr geometry, there is an additional effect. Your time does not only slow, it begins to twist. Because space-time is rotating, the future itself is dragged around the black hole. If you attempt to remain fixed in space, you will find that your future points in a direction that includes motion around the black hole. To move forward in time is to rotate. This is not a metaphor. It is built into the structure of the equations. Inside the Ergosphere, this becomes absolute. There is no path forward in time that does not involve angular motion. Time has acquired a direction in space. Deeper still, beyond the event horizon, this effect grows more extreme. The coordinate that once represented time becomes a kind of radial direction. Moving forward in time means moving inward toward the center. You cannot avoid it any more than you can avoid the future. But inside a Kerr black hole, the story does not end there. After crossing the inner horizon, the roles of time and space can change again. The equations allow regions where time becomes a spatial direction and space becomes temporal. In some of these regions, the coordinate that once represented rotation becomes the new time. This creates the possibility of paths where time seems to loop. This is the origin of the strange predictions about time travel in Kerr black holes. The mathematics allows closed time-like curves, paths through space-time that return to the same moment from which they started. In such a geometry, an object could in principle meet its own past. This does not mean that black holes are time machines in any practical sense. The extreme instability of the inner horizon likely destroys these paths. But the fact that the equations allow them is deeply important. It shows that rotation pushes space-time into a regime where our usual ideas about before and after no longer hold. Even outside the black hole, time behaves strangely. The dragging of space-time causes clocks at different positions to tick at different rates, not only because of gravity, but because of rotation. Two observers at the same distance from the black hole, but at different latitudes, will experience different flows of time. The twisting of space-time has created a time gradient around the black hole. Light emitted near a spinning black hole is also affected by this twisted time. Its frequency is shifted. Its phase is altered. Signals from the inner regions arrive stretched and distorted. This is one reason why the environments near black holes are so difficult to interpret. In the presence of a Kerr black hole, time is no longer a universal parameter. It becomes local. It becomes directional. It becomes part of the geometry rather than a background. This is one of the deepest lessons of general relativity. Time is not something that exists independently of the universe. It is shaped by mass, energy, and motion. When something as extreme as a rotating black hole exists, time itself is forced to behave in ways that have no parallel in everyday life. And if one could fall into such an object, these effects would not be abstract. They would be experienced directly. As an astronaut were to fall toward a rotating black hole, their experience of time would begin to diverge from the rest of the universe in dramatic ways. 2. Someone watching from far away, the astronaut would appear to slow down. Their motions would stretch. Their signals would take longer and longer to arrive. This is a familiar effect near any black hole. But near a Kerr black hole, something additional occurs. The astronaut would also appear to drift sideways, carried by the dragging of space-time itself. From the astronaut's own perspective, however, their clock would tick normally. They would not feel time slowing. What they would feel is motion. Even if they tried to fall straight inward, their path would curve. Their future would tilt around the black hole. They would find themselves rotating even if they had no initial spin. This leads to a strange kind of time dilation that depends on direction. Two astronauts falling into the same black hole on different paths could experience different flows of time. One moving with the spin would age differently from one moving against it. Time has become anisotropic. It has a preferred direction, set by the black hole rotation. As the astronaut crosses the event horizon, something even more unusual happens. The outside universe appears to speed up. Light from distant stars becomes blue-shifted. Events that would have taken years far away seem to unfold in seconds. The entire future of the universe is compressed into a finite span of proper time. This does not violate relativity. It is a consequence of how the horizon separates different regions of space-time. From the inside, The horizon is not a special place. There is no wall, no sudden shock, but it marks the boundary between two very different causal structures. Inside the horizon, the direction that once represented time now points inward. The singularity lies in the future. No matter what the astronaut does, they will move toward it. In a Kerr black hole, however, the singularity is not the end of the story. Beyond the inner horizon, the equations allow the future to open up again. Time may regain a spatial character. New directions may appear. Some paths may even avoid the singularity. This creates a bizarre picture. An astronaut falling into a rotating black hole might not be forced into a single final point. Instead, they might enter a region where time and space are tangled so deeply that new futures become possible. But this is where theory meets its limits. The inner horizon is unstable. Radiation falling in is amplified. Energy grows without bound. The astronaut would likely encounter a wall of intense gravitational turbulence. Whatever lies beyond may be so violent that no physical object could survive. Still, the possibility remains that time inside a Kerr black hole is not simply a one-way march toward destruction. It may be a maze. Even outside the black hole, the twisting of time has observable effects. The orbits of stars near the black hole center are altered. Their clocks tick differently depending on how they move. The timing of signals from pulsars orbiting black holes could reveal this effect. Time itself is being dragged. This is why Kerr black holes are such powerful laboratories. They do not just bend space, they bend time. They reveal that the flow of time is not fixed but shaped by gravity and motion. In the presence of extreme rotation, even the past and future can be twisted. The deeper meaning of time inside a rotating black hole reaches beyond any ordinary physical intuition. In our daily lives, time moves forward at a steady pace. It has a clear direction. Causes come before effects. But in the warped geometry of a Kerr black hole, time becomes something that can bend, stretch, and in some regions, even turn back on itself. The reason lies in the way rotation couples to the structure of space-time. In Einstein theory, time is not a universal clock ticking everywhere in the same way. It is a coordinate woven into the geometry of the universe. When space-time rotates, time rotates with it. Inside a Kerr black hole, the coordinate that represents time outside becomes mixed with the coordinate that represents angular motion. In some regions, this mixing is so strong that moving around the black hole is mathematically similar to moving forward or backward in time. This opens the door to closed time-like curves. A closed time-like curve is a path that leads back to the same event in space-time. In such a geometry, it would be possible to return to your own past. The equations of the Kerr solution allow such paths inside the inner horizon. This does not mean that time travel is physically possible. The extreme instability of the inner horizon likely destroys these delicate structures. Any real black hole is filled with radiation, gravitational waves, and quantum fluctuations. These disturbances may collapse the geometry into something more singular. Yet the fact that general relativity allows such behavior is profound. It shows that time is not a rigid backdrop. It is something that can be shaped by gravity in ways that break our intuitive understanding of cause and effect. Even if closed time-like curves never exist in reality, their presence in the equations tells us that our theory is incomplete. Somewhere between general relativity and quantum mechanics, there must be a deeper framework that prevents paradoxes while still describing extreme gravity. This is one of the reasons Kerr black holes are so important. They push physics to its limits. They reveal where our current understanding begins to crack. Time near a spinning black hole is not simply slow or fast. It is directional. It is twisted. It is part of the same dynamical structure that creates the ergosphere and the jets. In this sense, a Kerr black hole is not just a massive object. It is a machine that manipulates the flow of time. And yet, for all this strangeness, the outside universe remains orderly. Stars orbit, galaxies evolve, light travels. The chaos is confined behind the horizon. But what would it be like to actually fall into such a place? To fall into a rotating black hole is to enter a realm where gravity no longer feels like a simple pull. It becomes a combination of stretching, twisting, and relentless forward motion through space-time. An astronaut approaching a Kerr black hole would not simply be drawn inward. They would be swept into a spiral. Far from the black hole, the gravitational field feels almost ordinary. Objects fall as they would near any massive body. But as the astronaut draws closer, tidal forces begin to grow. These forces arise because gravity is stronger at the feet than at the head. The difference stretches the body. This effect is called spaghettification. In a non-rotating black hole, this stretching is aligned radially. You are pulled directly toward the center. In a Kerr black hole, the stretching is more complex. Because space-time is rotating, the tidal forces have both radial and sideways components. Your body is not just stretched, it is twisted. For very large black holes, especially supermassive ones, the tidal forces at the event horizon can be surprisingly gentle. You might cross the horizon without feeling anything dramatic at that moment. But inside, the gradients grow rapidly. The twisting and stretching becomes stronger as you move inward. Your view of the universe would become increasingly distorted. Light from behind you would be bent forward. Light from ahead would be bent around. The black hole would appear to wrap the sky around you. Stars and galaxies would smear into luminous arcs. Because of the rotation, the distortion would not be symmetric. One side of the sky would be dragged faster than the other. You would see the universe appear to swirl. As you pass through the Ergosphere, you would find that no matter how you try to orient yourself, you are carried along by the spin. You could fire your thrusters, but they would only change how fast you rotate, not whether you rotate. Your future has been claimed by the black hole. Inside the event horizon, escape is no longer possible, but the journey is not yet over. In a Kerr black hole, the interior is not a simple funnel to a point. It is a layered structure of warped space-time. As you fall deeper, the tidal forces become extreme. Every atom in your body would feel a different gravitational pull. The forces would tear molecules apart, then atoms, then even the nuclei. Long before reaching any singularity, you would be reduced to a stream of fundamental particles. Yet the equations suggest that some paths through a Kerr black hole might avoid the worst of this. Because the singularity is a ring, not a point, there may be trajectories that pass through its center without encountering infinite curvature. In those paths, the tidal forces might remain finite. This is one of the strangest features of rotating black holes. The geometry allows the possibility of surviving the singularity, at least in theory. But again, this idealized picture is likely destroyed by the instability of the inner horizon. The intense radiation piling up there would probably create a lethal environment. No known material could survive it. Still, the fact that the equations allow such paths tells us something about the nature of space-time. Rotation has created an interior that is not simply an end, but a maze. The astronaut falling into a Kerr black hole would experience a universe that becomes increasingly distorted, increasingly violent, and increasingly strange. Their future would be bent not only inward but around. And even inside, the black hole would not be still. As the astronaut continues inward, the twisting of space-time becomes the dominant sensation. The sideways drag grows stronger. Every attempt to move in any direction is curved. The body is not just stretched into a thin filament. It is wound into a spiral by the rotating geometry. This is very different from falling into a non-rotating black hole. There, all directions lead straight to the center. Here, there is always a sideways component. Even the direction of maximum stretching is tilted. The black hole is not crushing you symmetrically. It is tearing you apart while rotating you at the same time. Light behaves just as strangely. Photons emitted by the astronaut are bent into spirals. Some are flung outward, others loop around and fall back. the interior of the black hole becomes a hall of mirrors made of curved space-time. As the astronaut approaches the inner horizon, the environment grows increasingly violent. Radiation from the outside universe that fell in earlier is compressed. Its wavelength shortens. Its energy increases. This blue-shifted light forms a kind of wall. The closer you get, the more intense it becomes. This effect is not subtle. According to theoretical calculations, the energy density near the inner horizon can grow without bound. Even a tiny amount of incoming radiation becomes a torrent of destructive energy. The black hole interior becomes a place of unimaginable violence. This is why most physicists believe that the smooth passages predicted by the ideal Kerr solution are not physically realized. The inner horizon becomes a singular region of extreme curvature. The astronaut would not pass through a quiet ring into another universe. They would be obliterated by a storm of energy. Yet even this destruction is driven by rotation. Without spin, there would be no inner horizon to become unstable. The black hole would have a single central singularity. It would be simpler, but in some ways, less extreme. The Kerr black hole is extreme because it tries to be too much at once. It tries to collapse. It tries to rotate. The competition between these tendencies creates a geometry that is rich, violent, and unstable. From the outside, all of this is hidden. We see only the horizon and the light from the accretion disk. But inside, the black hole is a dynamic system, not a static end. The astronaut falling in would not simply vanish. They would be stretched, twisted, irradiated, and ultimately destroyed by the deepest forces of gravity and rotation. Even in death, they would become part of the black hole spin. Their angular momentum would add to the vortex. Their energy would feed the system. The black hole would refuse to be still. Would you like me to continue to part 3 of this chapter? As the last traces of the falling astronaut are torn apart and absorbed, the black hole continues its relentless rotation. Every fragment of matter that crosses the horizon adds its own tiny contribution to the spin. Even destruction becomes part of the cosmic whirlpool. Nothing is wasted. Everything is folded into the geometry of space-time. This is the true nature of a Kerr black hole. It is not simply an object that devours. It is a structure that transforms. Mass becomes curvature. Motion becomes geometry. The history of everything that falls in is encoded in the way space-time twists. Outside the horizon, this twist is visible in the motion of gas, the bending of light, and the power of jets. Inside, it creates horizons within horizons and singularities shaped like rings. All of it flows from the same cause: rotation. A non-rotating black hole is a simple thing by comparison. It has a single horizon and a single central singularity. Its space-time falls inward like a smooth funnel. A rotating black hole is a storm. Its space-time swirls. Its horizons split. Its interior becomes a labyrinth. The difference between these two cases is not just mathematical, it is physical. Almost every black hole in the universe is rotating. Almost everyone is a Kerr black hole. This means that the extreme physics we have been describing is not a rare curiosity. It is the normal state of black holes. When we observe quasars blazing across billions of light years, we are seeing the power of Kerr black holes. When we see jets drilling through intergalactic space, we are seeing space-time itself acting as a dynamical engine. The black hole that refuses to sit still is one of the most important objects in astrophysics. It shapes galaxies, it influences star formation, it drives some of the most energetic phenomena we know, and yet it remains hidden behind a simple dark boundary. The horizon conceals a universe of complexity. This duality is part of what makes black holes so fascinating. They are both simple and impossibly complex. They are defined by a few numbers, mass, and spin, yet they contain geometries that challenge our understanding of reality. The Kerr black hole stands at the edge of what physics can describe. It is where gravity, motion, and time come together in their most extreme form. And beyond what we have explored so far lie still more mysteries. The disks and jets that surround these objects, the ways we observe them, and the deeper questions they raise about quantum gravity and information. Around a spinning black hole, the universe builds one of its most violent and luminous structures. Long before any atom crosses the event horizon, it becomes trapped in a vast rotating disk of plasma. This accretion disk is not simply orbiting, it is slowly falling inward, shedding energy and angular momentum as it spirals toward the black hole. Friction between neighboring layers of gas turns motion into heat. Magnetic turbulence stirs the plasma into a churning storm. Temperatures rise to millions of degrees Celsius, and in the innermost regions to billions. At these extremes, the gas glows in X-rays and gamma rays, becoming one of the brightest objects in the cosmos. The closer matter orbits to the black hole, the more energy it can release. This is where spin becomes crucial. A non-rotating black hole allows matter to orbit only down to a certain distance before plunging in. A rapidly rotating Kerr black hole drags space-time with it, allowing stable orbits to exist much closer to the event horizon. The deeper the orbit, the steeper the gravitational well. This means more energy can be extracted from every kilogram of infalling matter. In a fast spinning black hole, more than a third of the mass energy of falling gas can be converted into radiation. No nuclear process in the universe is this efficient. This is why some galaxies outshine trillions of suns. Their light does not come from stars. It comes from matter being shredded and heated in the gravitational field of a Kerr black hole. But the disk is only the beginning. Threaded through this glowing plasma are magnetic fields. These fields are dragged inward with the gas. As the black hole rotates, it winds these magnetic lines tighter and tighter. They become twisted like rubber bands. Energy builds up in them. Eventually, that energy must go somewhere. The black hole becomes the anchor of a colossal electromagnetic engine. Near the poles of the black hole, the twisted magnetic fields form narrow channels. Through these channels, energy is released in the form of jets. Charged particles are hurled outward at nearly the speed of light. Radiation is carried with them. These jets punch through the surrounding gas and escape into intergalactic space. They do not fade quickly. Some jets remain coherent for millions of light years. They inflate giant lobes of radio-emitting plasma far from the host galaxy. They heat the space between galaxies. They prevent gas from cooling. They shape the large-scale structure of the universe. All of this power comes from spin. The black hole is not burning fuel. It is losing angular momentum. Its rotation is being converted into electromagnetic energy through the twisting of space-time and magnetic fields. This is the ultimate expression of the Penrose process in nature. The faster the black hole spins, the stronger the jets. The stronger the jets, the more influence the black hole has on its galaxy. This creates a feedback loop that governs cosmic evolution. When a galaxy feeds its black hole, the black hole spins up. As it spins faster, it produces stronger jets. Those jets heat and blow away the gas that feeds the galaxy. Star formation slows. The black hole starves. Its jets weaken. Gas can cool again. New stars form. The cycle repeats. In this way, Kerr black holes act as cosmic thermostats. They regulate the growth of galaxies. They prevent the universe from collapsing into a sea of stars too quickly. When astronomers look across the universe and see patterns in galaxy sizes, star formation rates, and black hole masses, they are seeing the imprint of these rotating gravitational engines. And now, for the first time in history, we are beginning to see these objects directly. As technology has advanced, humanity has begun to peer closer and closer to the hearts of galaxies. For decades, black holes were inferred only through their effects. Stars moved too fast. Gas glowed too brightly. Something invisible had to be there. But now the shadows of black holes themselves have been seen. In these images, the shape of the darkness carries the signature of spin. A rotating black hole does not cast a symmetric shadow. The twisting of space-time pulls light around one side more than the other. One edge of the shadow appears brighter. one side of the glowing ring is boosted by the motion of the accreting gas racing toward us at relativistic speeds. The geometry of a Kerr black hole is written directly into these patterns of light. By studying these distortions, astronomers can measure how fast black holes are spinning. They do this using several methods. One of them examines the inner edge of the accretion disk. The closer that edge is to the black hole, the faster the black hole must be rotating. Another looks at how X-rays reflect off the disk. The shape of certain spectral lines becomes warped by gravity and motion. The degree of warping reveals the spin. These observations have confirmed what theory predicted. Many black holes are spinning at astonishing rates. Some are rotating at more than 9/10 of the maximum speed allowed by relativity. These are not gentle whirlpools. They are nearly perfect space-time vortices. The Event Horizon Telescope has given us another window. By linking radio observatories across the Earth into a single planet-sized instrument, astronomers have imaged the shadow of a supermassive black hole. The size and shape of that shadow are consistent with a Kerr black hole, whose space-time is dragging light into curved paths. These observations are not just pictures, they are tests of general relativity in the strongest gravitational fields ever probed. So far, Einstein theory has passed every one of them, but these measurements do more than confirm known physics. They allow us to watch Kerr black holes at work. We can see how jets align with the spin axis. We can see how disks tilt and wobble. We can see how space-time itself guides matter into cosmic structures. In some systems, the accretion disk is not aligned with the black hole spin. The result is a warped disk that slowly precesses. This causes the jets to sweep across space like cosmic searchlights. Such behavior is only possible because space-time is being dragged by rotation. The universe is not just falling into black holes, it is being sculpted by their spin. When we observe quasars flickering, when we watch jets change direction, when we see disks flare with sudden bursts of light, we are watching the dynamic interaction between matter and rotating space-time. These are not distant abstract objects. They are engines that shape the observable universe. And through them, we are learning that gravity is not merely attraction. It is motion. It is geometry. It is a living structure that responds to mass and spin. The Kerr black hole stands as the clearest expression of this truth. As observations improve, Kerr black holes are becoming not just objects of theory, but laboratories for the deepest laws of physics. Every photon that escapes from near the event horizon carries information about the geometry it traveled through. Every ripple in spacetime from colliding black holes encodes the properties of their spin. By decoding these signals, scientists can test whether the universe truly obeys Einstein equations in the most extreme environments. When two black holes spiral together and merge, their spins interact. The final black hole that forms rings like a struck bell, emitting gravitational waves whose frequencies and decay times depend on its mass and spin. Detectors on Earth can measure these waves. From them, astronomers can reconstruct the nature of the newly born Kerr black hole. Once again, the results agree with the predictions of general relativity. These measurements are remarkable. They tell us that space-time really does behave like a twisted fluid around rotating black holes. They tell us that horizons and ergospheres are not just mathematical artifacts, they are physical. Yet these observations also point towards something deeper. The information carried by light and gravitational waves must be preserved. But black holes hide information behind their horizons. This leads to one of the greatest puzzles in physics, the black hole information paradox. A Kerr black hole adds another layer of complexity. Its interior structure is richer, its horizons are multiple, its geometry is dynamic. Understanding how information is stored, scrambled, and possibly released by a rotating black hole is one of the central challenges of modern theoretical physics. Some theories suggest that the horizon itself is not smooth but composed of quantum structures. Others propose that information is encoded in subtle correlations in the radiation emitted by black holes. In all of these ideas, spin plays a role. The rotation of spacetime affects how quantum fields behave near the horizon. In this way, Kerr black holes are not just astrophysical objects. They are gateways to quantum gravity. They sit at the intersection of relativity, quantum mechanics, and thermodynamics. The same object that powers quasars and shapes galaxies may also hold the key to understanding how the universe stores information. This is why the study of rotating black holes is so important. They are not just monsters in space. They are experiments run by nature itself, testing the deepest laws of reality under conditions no laboratory on Earth could ever create. And the more we observe them, the more they challenge us to rethink what space, time, and information really are. The Kerr black hole stands as the ultimate expression of gravity in motion. For most of human history, black holes were invisible in every sense. They were not even known to exist. They were mathematical curiosities buried deep inside equations. But in the last few decades, that has changed. We have not only found black holes, we have begun to see them. A Kerr black hole announces itself through motion. Stars orbit something they cannot see. Gas falls into something that emits no light. Jets erupt from something hidden. Every one of these signs points to a massive rotating object whose gravity is warping space-time. One of the most powerful tools for studying these objects is X-ray astronomy. The innermost regions of accretion disks glow in X-rays. These photons originate just a few gravitational radii from the event horizon. Their energy and timing are shaped by the spin of the black hole. By measuring how the X-ray brightness flickers and how its spectrum shifts, astronomers can map the motion of matter in the warped space-time around a Kerr black hole. A key technique is called X-ray reflection spectroscopy. High-energy photons from a hot corona above the disk strike the disk surface and are reflected. In that reflection appear sharp spectral features. Gravity and rotation smear and shift these features. The amount of smearing tells us how fast the black hole is spinning and how close the disk reaches to the horizon. In some systems, these measurements reveal disks that extend almost to the very edge of the event horizon. That means the black hole must be spinning rapidly. Space-time is being dragged so strongly that stable orbits exist extremely close to the point of no return. Another window comes from the Event Horizon Telescope. By combining radio observatories around the Earth, astronomers have created a telescope the size of the planet. With it, they have imaged the shadow of a supermassive black hole. This shadow is not the black hole itself, but the region of darkness created by light being bent and captured by the warped space-time. The shape of this shadow depends on spin. A rapidly rotating Kerr black hole produces a shadow that is asymmetric. One side is brightened by the motion of hot gas moving toward us. The other side is dimmer. This asymmetry is a signature of space-time being dragged. These observations have confirmed that real black holes are indeed Kerr black holes. They spin, they drag space-time, they match Einstein equations with extraordinary precision. Yet this is only the beginning of what we can see. As astronomers continue to refine these techniques, Kerr black holes are being measured with ever-increasing precision. In some systems, the spin can be determined to within a few percent. These numbers are not just abstract. They tell the story of how the black hole grew. A black hole that accreted matter steadily from a disk aligned with its rotation will spin up. Over millions of years, it can approach the maximum allowed by relativity. A black hole that grew through chaotic mergers or random infall will tend to have a lower spin. By reading the spin, we are reading the history of the galaxy itself. Gravitational waves add another powerful method. When two black holes spiral together, their spins affect the pattern of the waves they emit. Detectors on Earth can pick up these subtle imprints. From them, scientists can infer not only the masses of the black holes, but also how fast and in what directions they were spinning. These measurements have revealed that black holes in binary systems often have complex spins. Some are aligned with their orbits, others are tilted. This suggests violent pasts involving supernova explosions, stellar interactions, and multiple mergers. Each Kerr black hole carries the memory of these events in its rotation. Spin also affects how black holes eat. In a rapidly spinning Kerr black hole, the innermost stable orbit is closer to the horizon. This means matter can release more energy before falling in. Such systems shine more brightly for the same amount of accreted mass. By comparing luminosity and spin, astronomers can learn how efficiently black holes convert matter into radiation. This is why some quasars are so extraordinarily bright. They are powered by fast-spinning Kerr black holes that squeeze every possible drop of energy from the infalling gas. Even the orientation of jets is tied to spin. In many systems, the jets line up with the black hole rotation axis, rather than with the disk. This indicates that the black hole itself, not just the surrounding matter, is driving the outflow. The Kerr geometry is imprinting its structure on the large-scale universe. The more we observe, the more the picture becomes clear. Black holes are not simple spherical holes. They are spinning space-time engines, and now we can see them well enough to test that idea. The most striking confirmation of Kerr black holes came when the shadow of a supermassive black hole was imaged directly. The dark region in the center of the glowing ring is not the event horizon itself, but the imprint of photons that fell in and never returned. The size and shape of that shadow are determined by how space-time bends light. For a rotating black hole, this bending is not symmetric. Light approaching from one side is dragged along by the spin and can orbit longer before escaping. Light from the opposite side is more easily captured. The result is a shadow that is slightly lopsided. This is exactly what was observed. These images also show a bright crescent. That crescent is caused by the relativistic motion of the accretion disk. Gas moving toward us appears brighter because its light is Doppler boosted. Gas moving away appears dimmer. The pattern of brightness traces the direction and speed of rotation. In this way, the Kerr geometry is written directly into the light we see. But imaging is only one piece of the puzzle. Time variability provides another. The hot plasma near the horizon flickers. Bright spots orbit. Flares erupt. The timing of these events depends on how fast space-time is being dragged. By measuring these flickers, astronomers can map the motion of matter in the warped geometry. In some systems, periodic signals have been detected that correspond to material orbiting near the innermost stable orbit. The period of these signals reveals the spin. Faster spins produce shorter periods. Once again, the observations align with Kerr black hole predictions. Even the polarization of light carries information. As light travels through curved space-time and magnetized plasma, its polarization rotates. The pattern of polarization around a black hole encodes the structure of magnetic fields and the geometry of space-time. Recent observations have begun to map these patterns, revealing the twisted fields predicted by models of rotating black holes. All of these techniques together form a new science, black hole astronomy. And at its center lies the Kerr solution. We are no longer guessing how black holes behave. We are measuring it. As this new era of observation unfolds, Kerr black holes are becoming precise tools for testing the laws of physics. Every detail of their shadows, jets, disks, and gravitational waves provides a way to probe gravity in its most extreme form. If Einstein's theory were even slightly wrong, these objects would reveal it. So far, the universe has been remarkably consistent. The behavior of light near the horizon, the motion of matter in accretion disks, the pattern of gravitational waves from mergers, all match the predictions of rotating black holes described by general relativity. But scientists are not just checking whether the theory is right. They are looking for subtle deviations. Many ideas about quantum gravity predict tiny changes in how horizons behave or how space-time is curved near singularities. Kerr black holes are where those effects would be strongest. Some models predict that the shadow might be slightly different. Others suggest that the ringing of a newly formed black hole after a merger might have extra tones. By listening carefully to these cosmic bells, physicists hope to glimpse new physics. In this way, Kerr black holes have become the ultimate laboratories. They are far away, but they are extreme enough to reveal effects that no Earth-based experiment could ever see. The fact that we can now observe these objects at all is extraordinary. Only a few decades ago, black holes were theoretical. Now we are measuring their spin, watching their jets, and imaging their shadows. The black hole has stepped out of mathematics and into astronomy, and what it shows us is a universe where space and time are dynamic, where motion and geometry are inseparable, and where the most violent objects are also the most revealing. At the deepest level, what we are seeing when we observe a Kerr black hole is not just an object, but the shape of reality itself under extreme stress. The shadow is not a thing. It is a silhouette carved out of light by warped space-time. The bright ring is not a surface. It is the path of photons trapped in orbit by the gravitational whirlpool. The jets are not explosions. They are space-time rotation being converted into energy and motion. Every observation confirms the same truth. Spin is not a minor property of black holes. It is the defining one. Without spin, a black hole would be a quiet sink. With spin, it becomes a cosmic engine, a regulator of galaxies, and a testbed for the deepest laws of physics. The Kerr solution is not an approximation. It is the blueprint of the real black holes that populate the universe. By measuring spin, astronomers are measuring how space-time itself behaves when pushed to its limits. They are mapping how gravity and motion merge. They are watching geometry become dynamic. And in doing so, they are approaching one of the greatest frontiers of science, the place where Einstein theory must meet quantum mechanics. Kerr black holes are where that meeting will be forced. Their horizons hide information. Their interiors challenge causality. Their rotation stirs space-time into configurations that may not be allowed in a complete theory of physics. Yet the universe has built them anyway. When we look at the glowing ring around a supermassive black hole, we are seeing the boundary of the known. When we detect the tremor of space-time from two merging Kerr black holes, we are hearing gravity speak in its most extreme voice. And every one of these signals tells the same story. The black hole does not sit still. It spins, it drags, it transforms the universe around it. That is what we have learned by seeing a Kerr black hole. And now, there is only one place left to go. Into what they tell us about reality itself. A rotating black hole is not merely a cosmic curiosity. It is the most extreme physical environment the universe can create. Every Kerr black hole is a place where gravity, motion, and quantum fields are forced into a single violent geometry. In this region, space-time is not a quiet background. It is a living structure, twisting, flowing, and reacting to everything that enters it. At the event horizon of a Kerr black hole, the flow of space-time reaches the speed of light. Nothing inside can communicate with the outside. Yet quantum theory insists that information cannot be destroyed. This creates one of the deepest conflicts in all of physics. If matter falls into a black hole and disappears behind the horizon, what happens to the information it carried? Does it vanish? Does it remain encoded in the geometry? Does it leak out in subtle forms? The presence of spin makes this problem even more profound. A Kerr black hole has multiple horizons. It has an ergosphere where energy can be extracted. It has an inner horizon where space-time becomes unstable. Each of these regions interacts with quantum fields in different ways. Particles are created. Radiation is emitted. Entanglement spreads across horizons. One of the most important predictions of quantum theory in curved space-time is Hawking radiation. Black holes are not perfectly black. They emit a faint thermal glow due to quantum effects near the horizon. Over immense timescales, this radiation causes the black hole to slowly lose mass. For a rotating black hole, Hawking radiation is not just a gentle leak of energy. It also carries away angular momentum. Over trillions upon trillions of years, a Kerr black hole will spin down and approach a non-rotating state before finally evaporating. This slow evolution connects gravity, quantum theory, and thermodynamics. The black hole has a temperature. It has an entropy. Its horizon behaves like a physical surface, with microscopic degrees of freedom. These are not metaphors. They are precise mathematical results. Understanding how these quantum processes work in the presence of rotation is one of the great challenges of modern physics. As the Kerr black hole evolves through Hawking radiation, a profound question arises. If the black hole eventually evaporates completely, what happens to the information about everything that fell into it? Quantum theory demands that information is preserved, but the black hole horizon seems to hide it. This is the black hole information paradox. It has driven decades of debate and discovery. Some of the deepest ideas in theoretical physics were born from attempts to resolve it. One possibility is that information is stored on the horizon itself. According to this idea, the surface of the black hole contains microscopic degrees of freedom that encode everything that has fallen in. The black hole entropy, which is proportional to the area of the horizon, counts these hidden states. In a Kerr black hole, this horizon is not static. It is rotating, it is dragged, it is shaped by the spin. This suggests that the information stored on it is not just sitting still, it is being stirred and mixed by the geometry of space-time. Another idea comes from holography. In this framework, the physics inside a region of space can be described by a theory that lives on its boundary. A black hole is then a hologram. Everything that falls in is encoded on its horizon. If this is true, then a Kerr black hole is a rotating hologram. Its spin corresponds to currents and flows in the underlying quantum theory. The twisting of space-time becomes the twisting of information. These ideas are not abstract. They are being tested. The pattern of Hawking radiation, the way black holes ring after mergers, and the fine structure of their shadows may all carry signatures of how information is stored and released. The rotation of a Kerr black hole makes these tests richer. It introduces new channels through which information could escape. It changes how quantum fields behave near the horizon. It creates superradiance, a process in which waves can be amplified by extracting rotational energy from the black hole. Superradiance is a quantum cousin of the Penrose process. Certain waves scattered off a rotating black hole come back stronger than they went in. The extra energy comes from the black hole spin. This effect could reveal the existence of new particles and fields beyond those known today. In this way, Kerr black holes are not just astrophysical engines. They are particle detectors on a cosmic scale. The deeper physicists look into rotating black holes, the more they find connections to the fundamental structure of the universe. One of the most powerful ideas to emerge in recent decades is that space-time itself may be built from quantum information. In this view, geometry is not basic. Entanglement is. A Kerr black hole is a perfect testing ground for this idea. Its horizons divide space-time into regions that cannot communicate. Quantum fields on either side become entangled. The amount of entanglement is related to the area of the horizon. This is why black hole entropy scales with surface area rather than volume. Rotation adds another layer. It changes how entanglement is distributed. It creates flows of information around the horizon. It may even create channels that link the inner and outer regions in subtle ways. Some theories suggest that the interior of a black hole is encoded in the entanglement structure of the radiation it emits. If so, then the twisting of space-time in a Kerr black hole corresponds to a twisting of quantum correlations. This is not just philosophy. In models based on holography, rotating black holes are dual to quantum systems with angular momentum. By studying one, physicists can learn about the other. Gravity becomes a way of talking about quantum information. In these models, the inner horizon of a Kerr black hole is associated with a breakdown of simple entanglement patterns. The instability there reflects a scrambling of information. the black hole becomes the fastest scrambler in the universe, mixing information at a rate set by its temperature and spin. This idea has been supported by calculations. Kerr black holes appear to scramble information more rapidly than non-rotating ones. Spin makes them more chaotic. This chaos is not random. It is structured by the geometry of space-time. The way information is mixed mirrors the way space-time is twisted. In this sense, a Kerr black hole is not just a physical object. It is a computation being performed by the universe. It takes in information, it mixes it, it eventually releases it in a highly scrambled form through Hawking radiation. Understanding this process could reveal how time itself emerges from quantum mechanics. Would you like me to continue to part 4 of this chapter? When physicists talk about time emerging from quantum information, they are pointing to something profound. In many modern theories, time is not a fundamental ingredient of reality. It is a result of how quantum systems change and how information flows between them. A Kerr black hole, with its twisting horizons and rotating geometry, may be one of the clearest examples of this principle in action. Inside a rotating black hole, the geometry forces information into complex patterns. Entanglement is stretched and twisted. Correlations are dragged around by the spin. The usual notion of a single global time breaks down. Instead, time becomes something that depends on how information is organized. This may be why Kerr black holes allow such strange structures in their equations, including closed time-like curves and inner horizons. These features could be signals that the classical concept of time is failing. Quantum information may impose deeper constraints that smooth out these pathologies in the real universe. Some researchers believe that the instability of the inner horizon is a clue. It suggests that nature does not allow information to flow in ways that would create paradoxes. When the classical equations predict time loops, quantum effects intervene, creating turbulence that destroys those paths. In this view, the violent region inside a Kerr black hole is not a bug. It is a safeguard. It protects causality by scrambling information so thoroughly that no signal can be sent to the past. The outer horizon, on the other hand, may be a kind of information membrane. It absorbs incoming data and re-emits it in scrambled form through Hawking radiation. The black hole becomes a one-way filter that preserves information but hides it behind complexity. Spin plays a crucial role in this process. It increases the rate at which information is mixed. It enhances superradiance. It changes how quantum fields interact with the horizon. A Kerr black hole is a more efficient information processor than a non-rotating one. This suggests that the universe may be using black holes as part of its fundamental information economy. They are not just sinks, they are transformers. By studying how rotating black holes handle information, physicists hope to learn how space-time itself is built from quantum bits. As physicists push deeper into the nature of Kerr black holes, a remarkable realization has emerged. These objects are not just extreme gravitational systems. They are the closest thing the universe has to a laboratory for quantum gravity. Every rotating black hole compresses energy, curvature, and information into a region where all known theories must confront each other. In everyday physics, gravity is weak. Quantum effects dominate atoms and particles, while gravity shapes planets and stars. These two realms rarely meet. But inside a Kerr black hole, they collide. The curvature of space-time becomes so intense that even quantum fluctuations of the vacuum are amplified. The spin of the black hole twists these fluctuations into new patterns. Reality itself becomes unstable. This instability is not random. It follows precise mathematical rules. The geometry of a rotating black hole forces quantum fields into states that cannot exist elsewhere. Waves are stretched and squeezed. Particles are created and destroyed. Entanglement is generated and scrambled at astonishing rates. One of the most important consequences of this is the phenomenon of superradiance. When certain waves strike a Kerr black hole, they do not simply scatter. They are amplified. The black hole gives up some of its rotational energy to the wave. This effect is purely a result of space-time rotation. Superradiance has deep implications. It means that Kerr black holes are unstable to certain kinds of quantum fields. If a new particle exists with the right properties, a rotating black hole would begin to shed its spin by emitting those particles. Over time, the black hole would slow down. By observing how fast black holes spin, physicists can place limits on what kinds of new particles might exist in nature. In this way, Kerr black holes become detectors for new physics. They can reveal the existence of ultralight particles that cannot be produced in any laboratory. The absence or presence of high-spin black holes in the universe becomes a clue about the fundamental contents of reality. But superradiance is only one example. The entire structure of a Kerr black hole is sensitive to quantum effects. The horizon temperature depends on spin. The spectrum of Hawking radiation depends on rotation. The way information escapes depends on the twisting of space-time. Some theories suggest that the horizon of a Kerr black hole is not smooth. It is made of tiny quantum threads. These threads may be stretched and wound by the spin, creating patterns that determine how information is stored. The black hole entropy would then count these microscopic arrangements. Other theories propose that the interior of the black hole is encoded in the entanglement of the radiation it emits. In this picture, a Kerr black hole is a continuously evolving quantum system. As it spins and radiates, it updates the information it contains. This leads to a radical idea. The geometry of space-time inside a black hole may not be fundamental at all. It may be an emergent description of a deeper quantum process. The ring singularity, the inner horizon, and the ergosphere could be manifestations of how information is organized at the most basic level. Rotation plays a central role in this organization. By introducing a preferred direction and a flow, spin creates a structure in the quantum information. It gives rise to currents, vortices, and patterns that have geometric meaning. In holographic models, rotating black holes correspond to quantum systems with angular momentum. Their thermal behavior, their chaos, and their information scrambling can be calculated in a dual theory that has no gravity at all. This is one of the most powerful insights of modern theoretical physics. Gravity and space-time may be shadows of quantum information. A Kerr black hole is therefore not just a gravitational object. It is a map between two ways of describing reality. On one side is curved space-time. On the other is a sea of entangled quantum bits. The rotation of the black hole links these two pictures. This is why the inner horizon instability is so important. It may be telling us that the classical space-time description is breaking down because the underlying quantum system has become too chaotic. The black hole is scrambling information faster than space-time can remain smooth. This chaos is not destruction, it is transformation. The black hole takes in information in an orderly form. It mixes it. It releases it in radiation that looks random but is secretly structured. Over unimaginably long times, a Kerr black hole will evaporate. Its mass will decrease, its spin will slow, its horizons will shrink. Eventually, it will vanish, leaving behind only a cloud of radiation. If information is preserved, as quantum theory demands, then everything that ever fell into the black hole will be encoded in that radiation. This means that the black hole, despite its violence, is not an eraser. It is a processor. It takes the story of stars, planets, and even people, and translates it into correlations between photons. It turns matter into information. In that sense, Kerr black holes are not places where reality ends. They are places where reality is transformed into a different language. And because they spin, because they twist space-time and quantum fields together, they may be the most powerful translators the universe has. They are not just objects in space. They are engines of meaning at the deepest level. As the journey into Kerr black holes reaches its deepest point, what emerges is not merely a theory of gravity, but a vision of what reality itself might be made of. A rotating black hole is not just a collapsed star, it is the universe. pushed into a form where its most fundamental ingredients are forced to reveal themselves. In this place, space no longer behaves as a background. Time no longer flows in a simple line. Energy no longer remains confined to matter. Everything becomes geometry and information intertwined. A Kerr black hole is where the universe runs its most extreme experiment. It compresses mass into a region where space-time curves violently. It concentrates angular momentum until space itself spins. It creates horizons that divide what can be known from what cannot. And in doing so, it builds a laboratory where the deepest laws of nature are tested every moment. The most important lesson Kerr black holes teach us is that space-time is not passive. It responds, it moves, it stores energy, it carries information. The Ergosphere proves this. The rotation of the black hole drags space-time so forcefully that energy can be extracted from empty space. The universe itself becomes a fuel. This is not metaphor, it is literal. Magnetic fields anchored in space-time are twisted. Particles are flung outward. Jets stretch across millions of light years. A black hole no longer appears as a sink, but as a cosmic engine. It gives back to the universe even as it devours. But deeper than this lies something even more profound. The horizon of a Kerr black hole behaves like a thermodynamic system. It has entropy, it has temperature, it radiates. This means that a black hole is not just a gravitational object, it is also a statistical one. Its surface area counts microscopic states. These states are not made of atoms, they are made of something more fundamental, quantum information. In this picture, the event horizon is not just a boundary, it is a storage device. Every particle that falls in increases the number of ways the horizon can be arranged. The black hole remembers, not in the way a brain remembers, but in the way a complex system remembers through its structure. Rotation changes how this memory is stored. A Kerr black hole does not keep its information in a static pattern, it stirs it. The twisting of space-time mixes quantum states. Information is scrambled at the fastest rate allowed by the laws of physics. This makes rotating black holes the most powerful information processors in the universe. The inner horizon instability is a signal of this. The equations show that information falling inward is compressed and amplified. Correlations pile up. Geometry becomes turbulent. Classical space-time breaks down. What remains is not chaos, but quantum complexity. Some physicists believe that what we call the singularity is not an end, but a transition. It is where space-time dissolves into pure quantum information. The ring-shaped singularity of a Kerr black hole may represent a region where geometry no longer makes sense, but where information still exists. In this view, falling into a Kerr black hole would not mean being erased. It would mean being translated. Your atoms would be torn apart. Your energy would be absorbed. But the quantum information that makes you what you are would be woven into the black hole microstates. You would become part of its entropy, part of its story. And because black holes evaporate through Hawking radiation, that story would eventually be told again. Over immense timescales, photons and particles would carry your information back into the universe. Not in a recognizable form, not in a way that could reconstruct you, but in a way that preserves the fundamental rules of reality. This means the black hole is not a destroyer of information. It is a transformer. It converts matter into geometry, geometry into quantum states into radiation. Kerr black holes add another layer to this process. Their spin creates superradiance. Certain waves gain energy by interacting with the black hole. This allows information and energy to leak out in ways that non-rotating black holes cannot. Rotation opens channels in the fabric of space-time. These channels may be how the universe enforces its deepest conservation laws. They may be how causality survives. They may be how quantum mechanics and gravity remain compatible. In modern theories, space-time itself may be built from entanglement. The way quantum bits are connected determines the shape of space. A Kerr black hole, with its twisting horizons and ergosphere, would then be a region where entanglement is wound into a vortex. Geometry becomes the visible form of quantum information in motion. This is why rotating black holes are so important. They are not just massive objects, they are blueprints of how reality organizes itself. Every orbit of a star around a black hole, every flare from an accretion disk, every jet that pierces a galaxy is a message from this deeper layer. It tells us that the universe is not a collection of things. It is a network of relationships, constantly being reshaped by motion and gravity. A Kerr black hole is where those relationships are stretched to their limit. It is where time becomes direction, where space becomes current, where matter becomes memory. If the universe has a place where it reveals what it is truly made of, it is here, inside the rotating heart of a Kerr black hole. At the end of this journey, there is no explosion, no final collapse, no moment where everything suddenly stops. There is only a slow, steady realization that the universe is far stranger and far more beautiful than it first appears. The Kerr black hole, the rotating heart of darkness we have followed through twisted space-time and broken time itself, is not an aberration. It is a natural expression of how reality behaves when pushed to its limits. For most of human history, the night sky seemed calm and distant. Stars were fixed points. Galaxies were faint smudges. Space was a quiet stage on which the cosmos unfolded. But now we know that beneath that apparent stillness lies a universe in constant motion. Everything spins, everything flows. Even space-time itself is alive with movement. A Kerr black hole is the ultimate proof of this. It is a place where rotation is so intense that the universe can no longer hide its true nature. Space is dragged, time is twisted, light is bent into spirals. Matter becomes energy, and energy becomes geometry. In the presence of such an object, the simple idea of a background vanishes. There is no neutral frame, no fixed reference, no still point in the storm. Reality itself is in motion, yet despite this violence, there is order. The same equations that describe the gentle orbit of planets describe the ferocious whirlpool around a black hole. The same laws that govern a falling apple govern the fall of light into an event horizon. The universe is not chaotic at its core. It is consistent. It follows rules even in its most extreme expressions. What makes Kerr black holes so powerful is not just their gravity, but their ability to reveal these rules. They are natural laboratories, created by the collapse of stars and the growth of galaxies, where physics is tested at energies and curvatures far beyond anything humanity can build. Every photon that escapes from their disks, every jet that erupts from their poles, every ripple of space-time from their mergers carries information about how the universe truly works. In their shadows, we see the imprint of space-time itself. In their jets, we see the conversion of geometry into motion. In their radiation, we see the whisper of quantum mechanics at the edge of gravity. These are not separate phenomena. They are different faces of the same underlying reality. Perhaps the most profound lesson Kerr black holes teach us is that the universe does not destroy. It transforms. Matter that falls into a black hole does not simply vanish. It becomes part of a larger structure. Its mass adds to curvature. Its motion adds to spin. Its information becomes encoded in the horizon, even when a black hole slowly evaporates over unimaginable timescales. That information is not erased. It is released, scattered across the cosmos in the form of faint radiation, woven into the future of everything. This is a universe that remembers. It remembers through entanglement. It remembers through geometry. It remembers through the subtle correlations that persist, even when all visible traces are gone. In this sense, a Kerr black hole is not a grave. It is a library written in the language of space-time itself. And like any library, it does not keep its books in neat rows. It scrambles them, it reorders them, it hides them behind complex patterns. But the stories remain. The rotating nature of these black holes makes this even more true. Spin creates currents in space-time. It mixes information. It spreads correlations across horizons. It ensures that nothing remains isolated. Everything becomes part of a larger dynamic whole. When we look at a distant quasar blazing across billions of light years, we are not just seeing a powerful light source. We are seeing the universe recycling its own substance. A star collapsed long ago. A black hole formed. Matter fell in. Energy was released. Galaxies were shaped. The story continues. When we detect gravitational waves from two Kerr black holes merging, we are not just hearing a cosmic collision. We are listening to space-time itself ringing, announcing a new configuration of mass and spin, a new chapter in the cosmic record. These events remind us that nothing in the universe is static. Not stars, not galaxies, not even the fabric of reality. Everything is in flux, guided by laws that are both simple and endlessly rich. In this light, the Kerr black hole becomes something more than an object of fear or mystery. It becomes a symbol of the universe's ability to organize complexity from collapse. It shows how even the most destructive processes give rise to new structures, new energies, and new possibilities. There is a quiet beauty in this, a sense that the universe, even in its darkest places, is not hostile. It is creative. It takes what falls and makes something else from it. We began with the idea of a black hole that refuses to sit still. That refusal turns out to be the key. Motion is not a flaw. It is the engine of existence. Without spin, without flow, without change, there would be no stars, no galaxies, no life. The Kerr black hole simply takes that truth to its extreme. It reminds us that stillness is an illusion. Beneath every surface, something is moving. And perhaps that is the final lesson. The universe is not a collection of things, but a network of processes, a dance of energy and information, a continuous unfolding of geometry and motion. In that dance, Kerr black holes are among the most powerful performers. They bend the rhythm, they twist the steps, they reveal patterns that are hidden everywhere else. By studying them, by imaging their shadows, by listening to their waves, by decoding their light, we are not just learning about black holes, we are learning about ourselves, about where we came from, about what the universe is made of, about how deeply connected everything truly is. The rotating heart of a Kerr black hole may be dark, but it is not empty. It is filled with structure, with information, with the imprint of everything that has ever fallen into it. And as long as the universe continues to spin, that story will never truly end.